Initially, the universe existed as an infinitely dense mass of matter. This mass underwent an explosion, leading to the formation of particles, atoms, stars, and galaxies that we observe today. For many years, this concept of the Big Bang has been the prevailing explanation. However, recent research has introduced a new perspective, suggesting that the universe may not have had a singular beginning as previously believed. Instead, it could be part of an endless cycle of expansion and contraction, continuously repeating itself. Prominent physicist Brian Cox is skeptical of the Big Bang theory, arguing that something cannot emerge from nothing. This skepticism adds an intriguing layer to the discussion, especially in light of recent findings from the James Webb Space Telescope, which have cast doubt on the idea that the Big Bang marked the definitive origin of the universe. This raises a fundamental question. If the Big Bang wasn't the beginning of the universe, what was? Let's embark on a journey to explore the origins of the universe, where we'll examine the limits of the Big Bang theory and seek answers to this profound question. If you want to stay updated on cosmic discoveries, don't forget to subscribe to our channel, like this video, share it with others, and turn on notifications. Scientists have developed a detailed understanding of the universe's early stages, encapsulated in the Big Bang theory. According to this model, the universe was once far smaller, hotter, and denser than it is today. Around 13.8 billion years ago, all the components of our reality were formed in a matter of minutes. In this theory, the universe, including stars and galaxies, was once incredibly tiny, about the size of a peach, and had a temperature exceeding a quadrillion degrees. Surprisingly, this narrative aligns consistently with all current observations. Astronomers have studied everything from the residual electromagnetic radiation of the early universe to the abundance of the lightest elements, and the results have matched the predictions of the Big Bang theory. Despite its apparent robustness, we know that the Big Bang theory doesn't fully explain everything. There is a missing piece in the puzzle, which lies in understanding the very first moments of the universe. This challenge is largely due to the limitations of our current theoretical frameworks. While general relativity and high-energy particle physics offer valuable models, the mathematical complexity increases as we probe deeper into the universe's beginnings, reaching a point where our existing methods can't provide clear solutions. One indication of this difficulty is the concept of a singularity, a point of infinite density at the beginning of the Big Bang. This notion suggests that the universe was once compressed into an incredibly small, dense state, which seems paradoxical. To solve this problem, we need to explore new frontiers in physics, developing theories that surpass these limitations and offer a more complete understanding of the universe's origins. Our current theories and methods are not robust enough to tackle this challenge, and new physics must be developed to integrate gravity and the other fundamental forces at extremely high energies. This is where string theory comes into play. String theory aims to unify gravity with the other fundamental forces, especially at ultra-high energies. It proposes that it can explain the earliest moments of the universe. One of the ideas that emerge from string theory is the concept of an aeon, derived from the Greek word meaning age or generation. This idea suggests that the Big Bang, as we understand it, may have been the result of a prior event, implying that it was not the definitive beginning but rather part of an ongoing process. Building on this concept, a related theory known as cyclic cosmology has emerged. Although the idea of a cyclic universe has been considered for centuries, string theory provides a solid mathematical foundation for it. In cyclic cosmology, the universe continuously oscillates between phases of expansion and contraction in an infinite cycle stretching both into the past and future. This theory was proposed by the renowned physicist Roger Penrose, who won the Nobel Prize for his work in this field. Penrose was intrigued by the remarkable mathematical relationship between the early universe, characterized by extreme density, heat, and smallness during the Big Bang, and the future state of the universe, which is expected to be cold, expansive, and devoid of matter. According to cyclic cosmology, these two states, hot and dense during the Big Bang and cold and empty in the far future, become mathematically indistinguishable when pushed to their extremes. Though it may seem counterintuitive, the complete absence of matter could be the key to the creation of all the matter we observe today. From this perspective, the Big Bang arises from what is left after all the matter in the universe has been consumed by black holes, eventually vanishing into dispersed photons in an immense void. The universe then emerges from what is, in essence, close to nothingness, but still a form of something, an actual universe though empty. The mystery lies in how this state of nothingness can be understood as both a cold, void universe and a dense, hot one, depending on how it is viewed. The key to understanding this paradox lies in a complex mathematical procedure called the conformal transformation, a mathematical change that alters the size of an object while preserving its shape. Roger Penrose demonstrated that the cold, empty state and the hot, dense state can be connected through this transformation, adjusting their spatiotemporal structures despite their differences in size. Penrose argues that time loses its conventional meaning under these extreme conditions. In cyclic cosmology, the transition from an old, cold state to a younger, hot one doesn't follow the usual sequence of events because, in these extreme states, both size and time lose their normal significance. The cold, empty state and the hot, dense state exist on separate timescales, meaning that, from the perspective of an observer within each state, the cold void would appear to last forever. In this realm of cyclic cosmology, physics and philosophy intertwine, offering both theoretical and detailed explanations for the origins of these cycles. Yet, even if Penrose's ideas gain traction within cosmological research, a deeper philosophical question remains. How did these cycles themselves originate? What is the true beginning of physical reality? The remarkable development of spacetime in the early universe may have prompted the creation of pocket universes within a larger multiverse. Each pocket universe would have unique properties shaped by random quantum fluctuations during the inflationary epoch. While the multiverse theory remains theoretical and difficult to test observationally, it provides a compelling explanation for the fine-tuning problem in cosmology. The apparent improbability that the fundamental constants of nature are perfectly calibrated to allow for the existence of complex structures like stars, galaxies, and life itself. Another intriguing concept that challenges traditional views of cosmic origins is eternal inflation, proposed within the framework of inflationary cosmology. This idea suggests that the universe undergoes a continuous cycle of inflationary phases, each leading to new regions of spacetime that may follow different physical laws. In this scenario, our observable universe is just one of countless regions within an ever-expanding cosmic foam. The notion of eternal inflation raises profound questions about the nature of time and causality in the multiverse. If inflationary bubbles continuously spawn new universes, the idea of a singular beginning or ultimate origin becomes increasingly elusive. Instead, the universe appears as a dynamic, ever-evolving entity embedded within a larger cosmic structure of ongoing inflationary development. In recent years, advancements in theoretical physics have spurred interest in alternative cosmological models that challenge the conventional narrative of the universe's origins. For example, some researchers have explored the possibility of a cyclic universe, where the Big Bang is not a one-time event but part of an endless cycle of expansion and contraction. According to cyclic cosmology, the universe undergoes repeated cycles of creation, evolution, and destruction, each ending in a cosmic collapse, followed by a new Big Bang. This idea draws inspiration from ancient cosmological concepts and modern theoretical frameworks like string theory, which posits that fundamental particles are not point-like objects but rather tiny vibrating strings of energy. The cyclic universe model naturally arises from certain solutions within string theory, which suggests that the universe might exist in a higher-dimensional spacetime where patterns of expansion and contraction result from the interplay of fundamental forces. While the cyclic universe theory remains speculative and faces significant challenges in terms of observational evidence and theoretical consistency, it offers a bold attempt to reconcile quantum mechanics with general relativity on cosmological scales. By proposing an eternal pattern of cosmic renewal, cyclic cosmology presents an intriguing possibility of a universe without a definitive beginning or end, where each cycle builds upon the remnants of its predecessor. In addition to theoretical models, observational cosmology has provided crucial insights into the early universe and its evolution over cosmic time. The discovery of the cosmic microwave background (CMB) radiation in the mid-20th century offered strong evidence for the Big Bang theory, providing a snapshot of the universe when it was only 380,000 years old. Detailed measurements of the CMB by satellites like the Planck Observatory have allowed scientists to map temperature and density fluctuations across the early universe with remarkable precision. Moreover, observational cosmology has revealed the large-scale structure of the universe, uncovering the intricate web of galaxies, clusters, and cosmic filaments that stretch across billions of light-years. By studying the distribution of galaxies and measuring their redshifts, astronomers have been able to trace the expansion history of the universe and determine its age, structure, and ultimate fate. One of the most astonishing discoveries in observational cosmology is the existence of dark energy, a mysterious form of energy that permeates the universe and is driving its accelerated expansion. First detected in the late 1990s through observations of distant supernovae, dark energy constitutes about 68% of the total energy density of the universe, making it the dominant component of the cosmic energy budget. The nature and origin of dark energy present a major challenge to our current understanding of fundamental physics, as its cause remains poorly understood. Several theories suggest that dark energy could be related to the vacuum energy predicted by quantum field theory, while others propose modifications to Einstein's theory of general relativity to explain the observed acceleration of the universe. In parallel with observational efforts, experimental physicists are actively searching for new particles and interactions that could offer clues to the true nature of dark energy. Additionally, major projects like the Large Hadron Collider (LHC) are designed to probe the frontiers of particle physics by colliding protons at high energies, potentially revealing new physics beyond the Standard Model. Advances in astrophysical instrumentation have also enabled researchers to explore the universe across different wavelengths of the electromagnetic spectrum, from radio waves to gamma rays. Observatories such as the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Hubble Space Telescope have revolutionized our understanding of star formation, galaxy evolution, and the cosmic distribution of dark matter. Looking ahead, the next generation of observatories such as the James Webb Space Telescope, JWST, and the Square Kilometre Array, SKA, promises to provide even deeper insights into the early universe and its fundamental components. These cutting-edge instruments will allow scientists to study the first galaxies, investigate the epoch of reionization, and search for traces of primordial gravitational waves left over from the Big Bang. In conclusion, the quest to understand the origins of the universe presents one of the greatest intellectual challenges of our time. From ancient myths and philosophical inquiries to modern scientific theories and observational discoveries, humanity's exploration of the cosmos has yielded profound insights into the nature of reality itself. As we continue to push the boundaries of knowledge and exploration, new theoretical models, observational techniques, and experimental innovations will undoubtedly shed light on the fundamental mysteries of existence and our place in the universe. This brings us to reflect on the justification for the existence of something rather than nothing, one of the most profound questions in philosophy and science. For the purposes of this discussion, we'll focus on explanations within the realm of physics, considering three possible scenarios for the origins of these phenomena. First, there may be no obvious reason at all. Second, there could be an infinite series of cycles, where each cycle represents a different universe, with the initial quantum state of each universe determined by some aspect of the preceding one. Finally, there's the possibility of a single cycle in a repeating universe, where the beginning of each cycle is explained by some component of its own end. These possibilities are intriguing because they avoid the need for uncaused events, offering a more intricate explanation within the framework of physical laws. Penrose introduces the idea of an infinite series of cycles influenced by his interpretation of quantum mechanics. In quantum mechanics, a physical system exists in multiple states simultaneously until it is observed, at which point it randomly collapses into one state. Penrose suggests that each cycle is influenced by random quantum events that introduce variations between cycles. This idea opens up exciting possibilities for experimental physicists, as it implies the potential to detect subtle traces or anomalies in the afterglow of the Big Bang. The quest to understand the origins and nature of the universe has been a central pursuit of human curiosity and scientific inquiry for centuries. From ancient philosophical theories to modern cosmological models, humanity has continuously sought to unravel the mysteries of existence itself. In contemporary astronomy and cosmology, the study of the universe's origins has led to significant discoveries and captivating theoretical frameworks that challenge our fundamental understanding of time, space, and matter. One of the enduring questions that has captivated both physicists and cosmologists is the nature of the universe before the Big Bang. While the Big Bang theory provides a compelling explanation for the evolution of the universe from a hot, dense state to its current expansive structure, it leaves the question of what came before this monumental event open. The concept of a pre-Big Bang era raises important philosophical and scientific implications, pushing the boundaries of our knowledge and challenging several theoretical principles. Various hypotheses have been proposed to address this question, each offering unique insights and perspectives on the early universe. One such idea is the concept of the multiverse, which posits the existence of a vast ensemble of universes, each with its own distinct physical properties and fundamental constants. In the multiverse framework, our universe is just one among many, each emerging from different initial conditions and governed by its own set of physical laws. The idea of a multiverse naturally arises from certain interpretations of quantum mechanics and cosmological inflation. According to inflationary cosmology, the rapid expansion of space in the early universe set the stage for the creation of multiple, distinct universes.